Hi, this is Ben with Snake on a Stick Medical Videos. Today we're going to be talking about potassium-sparing diuretics. The first thing I want to talk about is how potassium-sparing diuretics actually affect the acid-base balance in the body. In order to understand this, we actually have to do a little bit of renal physiology. So what I'm drawing here is the general structure of the cortical collecting tubule, showing the lumen here and the interstitial space here. The two main cells in this area of the kidney are the principal cell and the intercalated cells. So the lumen of the cortical collecting tubule, that's going to be where the urine is. So what does the principal cell do? It actually is responsible for absorbing sodium, secreting potassium, and absorbing water through aquaporins. Okay, aquaporins here. And then you have your basolateral sodium-potassium pump or exchanger, which is pretty ubiquitous throughout the body. What I'm drawing here is the V2 receptor, which the ADH or vasopressin acts upon and releases stored aquaporins to the luminal side of the membrane and encourages water absorption. What I'm drawing here is the aldosterone receptor. So this is the aldosterone receptor. Remember, the aldosterone receptor is actually within the cell because it's aldosterone doesn't have a cell surface receptor. What I'm showing here is the aldosterone receptor actually upregulates that sodium channel, that potassium channel, and that sodium-potassium ATPase pump. The alpha intercalated cell is responsible for a few different things. It'll secrete H+ and reabsorb potassium. So in terms of potassium, it's the opposite of the principal cell. It has a basolateral exchanger here, but that's for bicarbon chloride. Okay, so why is this important? So if we go back to the principal cell, there are two drugs you might have heard of: triamcinolone and amiloride, and also you have two other drugs known as eplerenone and spironolactone. These are all your potassium-sparing diuretics. The triamcinolone and amiloride actually affect the sodium channel, whereas the eplerenone and spironolactone, they block the aldosterone, specifically via the aldosterone receptor. What I'm highlighting here is that aldosterone's main function is to take potassium and hydrogen ions and put them in the urine. It'll actually help the body reabsorb the sodium. Okay, so what effects do potassium-sparing diuretics have on acid-base balance in the body? So how can we first start thinking about this? So let's go back to aldosterone's main effects in the cortical collecting tubule. Remember that we said that aldosterone's effects are to secrete potassium and to secrete hydrogen ions into the lumen of the tubule and to reabsorb sodium. So what you're going to have is you're going to have a push of potassium and push of hydrogen into the tubule. You're going to have a drawing in of sodium back into the body. So this is what I'm showing, is that aldosterone causes hydrogen ions to leave the body, okay? So I'm pushing those hydrogen ions out of the body. So blocking aldosterone actually causes the H+ ions to stay and can cause acidosis. So K+ sparing diuretics cause acidosis. There's actually an additional factor to this that I wanted to highlight as well. And this has to do with tissue cells or generic tissue cells throughout the entire body. On a lot of cells in the body, you actually have this potassium and hydrogen ion exchanger here. And so what this potassium and hydrogen ion exchanger here will do is it'll take potassium and it'll put it inside the cell, and it'll then spit out hydrogen into the interstitium or the rest of the body. So what I'm saying here is the cells have this K+, H+ exchanger. In K+ sparing diuretics, you're actually going to have hyperkalemia. So remember, if we block that aldosterone mechanism, we're going to have retention of the potassium. And this will actually raise the serum or the body potassium. The serum or body's potassium will actually cause a movement to the intracellular space, and that'll cause a movement of hydrogen ions out of the intracellular space. So what's going to happen is that basically you're going to have an additional factor exacerbating acidosis. So to summarize here, we have, remember, the two main cells in the cortical collecting tubule, the principal cells and the alpha intercalated cells. The principal cells are responsible for sodium reabsorption, K+ excretion, and also that aquaporin and H2O reabsorption. The aquaporin insertion, actually. Okay, remember that was mediated by vasopressin or ADH via V2 receptor. Remember the alpha intercalated cells, they are responsible for H+ secretion and K+ absorption. So that's what they do. Aldosterone, remember, it causes H+ to leave. So K+ sparing diuretics, which actually block aldosterone's action, they make it stay. They make the H+ to stay, causing the body to have an acid-like state. So that's how you can remember that. Thanks for listening.